Good evening, students. In the last class, we discussed the first part of compact metric space. Now, we discuss the second part of compact metric space. In the second part, we start with sequentially compact metric space. Sequentially compact metric space. A metric space XD is called sequentially compact. A metric space XD is called sequentially compact if every sequence xn in X, every sequence in X has a convergent subsequence. So sequentially compact means every sequence in the matrix space must have a convergent subsequence. Then we call that metric space as sequentially compact metric space. Okay, next theorem related to sequentially compact metric space. Theorem is every sequentially compact metric space is complete. Sequentially compact metric space is complete. Sequentially compact metric space is complete. So first we consider XD be a sequentially compact metric space. Then for every sequence xn, it must have a convergent subsequence. And complete means every Cauchy sequence in X must be convergent. So first we assume that xn be a Cauchy sequence in X. We have to prove xn is convergent. Now xn is a Cauchy sequence means xn is any sequence. And as it is sequentially compact, xn must have a convergent subsequence, that is xnk. So xnk is convergent. Now as xn is a Cauchy sequence, then the condition is d of xn plus p xn less than epsilon by 2 for all n greater than equal k1 and for all p greater than equal 1. And xnk is convergent, so another condition is d of xnk x less than epsilon by 2 for all nk greater than equal k2. Let k equals to max of k1 and k2. K equals to max of k1 k2, that then d of xn x, that is less than equal d of xn x n plus p, or rather xn k plus d of xn k x. This is less than epsilon by 2 by the definition of Cauchy sequence, plus epsilon by 2 by definition of convergent equal to epsilon for all n greater than equal k. Thus, the sequence itself is convergent. So every sequence in X, every Cauchy sequence in X is convergent, so it becomes a complete metric space. Okay, next is definition, Bolzano-Weierstrass property. A metric space is said to satisfy Bolzano-Weierstrass property. A metric space is said to satisfy Bolzano-Weierstrass property if every infinite subset of X has a limit point. Every infinite subset of X has a limit point. Now the important theorem is sequentially compact if and only if metric space satisfies Bolzano-Weierstrass property. So first we consider xn be sequentially compact. We assume that it is sequentially compact. We have to prove it satisfies Bolzano-Weierstrass property. Bolzano-Weierstrass property means every infinite subset must have a limit point. So we consider a sequence as it is sequentially compact, so the sequence must have a convergent subsequence, say xnk. Therefore, d of xnk x less than epsilon for all n greater than equal k. Okay, now we prove it satisfies Bolzano-Weierstrass property. Now let A be an infinite set. From the infinite set, we choose an element, say A1. As it is still infinite, we consider another point A2. Still it is infinite, so we choose another point A3. In that fashion, we can construct a sequence an from A. From A means from x also. So we get a sequence xn. As it is sequentially compact, so it must have a convergent subsequence. So we call it ank that converges to A. So d of ank A less than epsilon, that is ank belongs to S epsilon A. Now ank is a member of A, so we say that S epsilon A intersection A minus A not equals to phi. That indicates that A is the limit point, small a is the limit point of capital A. So infinite set has a limit point, so it satisfies Bolzano-Weierstrass property. Now next part, we assume that metric space satisfies Bolzano-Weierstrass property. That means every infinite set has a limit point. Now we have to prove it is sequentially compact. So for that, we consider xn be any sequence. We have to prove it is sequentially compact. That is, we have to prove it must have a convergent subsequence. So xn is any sequence, and let B be the trace of xn, and we assume that B is infinite. As B is infinite, so by Bolzano-Weierstrass property, B has a limit point, say x. Then for every positive integer n, S 1 by n x intersection B minus x not equals to phi for every n. That means we get its element x n dashed belongs to S 1 by n x. So x n dashed is an element of B minus x. That is, x n dashed is a part of the sequence because trace contains all the members of sequence. So x n dashed is a part of the sequence. So we get a subsequence x n dashed of the sequence xn. And as it satisfies this condition, so we say that d of x n dashed x less than 1 by n, that tends to 0 as n tending to infinity. So the subsequence is convergent. So the sequence has a convergent subsequence, so it satisfies Bolzano-Weierstrass property. That is the theorem. If a sequence satisfies, if a metric space is sequentially compact, so it satisfies Bolzano-Weierstrass property, and if it satisfies Bolzano-Weierstrass property, then it is sequentially compact. Next important theorem is very important theorem. Every compact metric space is sequentially compact. Compact metric space is sequentially compact. So we consider XD be a compact metric space. Okay. Now we prove that it is sequentially compact. As sequentially compact and Bolzano-Weierstrass property are synonymous, so we now prove that it satisfies Bolzano-Weierstrass property. That means every infinite set must have at least one limit point. So we consider A be an infinite set, and we have to prove A must have a limit point. Now we start with the contradiction. Assume that A has no limit point. That means for each A belongs to capital A, as A is not the limit point, there exists a positive real number R such that SRA intersection A equals to phi. So we say that SRA intersection A minus A equals to phi, because A is not the limit point. So rather we say that SRA contains at most the point small a of the set capital A. So SRA maximum contains small a of capital A. Now the collection SRA such that A belongs to X, that must covers X. Now X is compact, so this cover must have a finite subcover. So S R1 A1, S R2 A2, S Rn An, that covers X, and as A is a subset, so that also covers A, and the condition is this open sphere contains exactly the center of A. So A becomes at most A1, A2, An. So now A becomes finite, which is a contradiction because we consider A is infinite. So why the contradiction arises? Because we consider A has no limit point. So A must have a limit point. That means the metric space satisfies Bolzan-Weierstrass property. Otherwise, metric space is sequentially compact. So every compact metric space is sequentially compact. Every compact metric space is sequentially compact. The converse is also true. That is, every sequentially compact metric space is also compact. This is your homework. Now next definition is epsilon net. Now what is epsilon net? Let XD be a metric space and epsilon is any positive real number. A is a subset of X. Now if the collection of open sphere with radius epsilon and center from A covers X, then the set A is called an epsilon net. So what is epsilon net? It is a subset of the metric space. And why we call that subset as epsilon net? Because we choose a point from the set A and radius epsilon fixed, then the collection of all such open sphere, if it covers X, then A is called epsilon net. Okay, now next, let XD be a next theorem. Let XD be a metric space and A be any subset of X. Next theorem is XD be a metric space and A be a subset of X, then A is dense if and only if A is an epsilon net. Okay. Now first part, let A be an epsilon net. We assume that A is an epsilon net of X. We have to prove A is dense. That is we have to prove closure of A equals to X. Now first part, as A is a subset of X, then A closure is also a subset of X. So this is equation 1. Now next we consider an element X from capital X. Now as A is the epsilon net, then for X there exists an element A belongs to A such that X belongs to S epsilon A. Therefore D of XA less than epsilon, or A belongs to S epsilon X. Now if X equals to A, then X also belongs to A. That is, the proof is complete. Otherwise, if X does not belongs to A, then that indicates that A's epsilon X intersection A minus x not equals to 5, that means x is the limit point of A, so x belongs to A dash, that is derived set, or x belongs to A closure. So capital X subset of A closure. This is equation 2. From 1 and 2 we have capital X equals to A closure, so A is dense. So A is epsilon net means A is dense. Now converse part, let me assume that A is dense. So A closure equals to X. Then for each X, we have x belongs to A closure. Now x belongs to A closure means x is either the point of A or the limit point of A. Therefore, we say that for every r greater than 0, is Rx intersection A not equal phi. Therefore, we can choose the point A that means d of xa less than r for all r, or x belongs to S A R. Therefore, every point of x contained in an open sphere whose center is in the set A and radius is r, that means, and this is true for every r, that means A is the epsilon net, or rather R net. So A is the R net. Next definition, totally boundedness. Totally boundedness means XD be a metric space and A be any non-empty subset. The subset is called totally bounded if it has a finite epsilon net. That means it has an epsilon net which contains finitely many elements. Now next important theorem is totally boundedness implies boundedness. So let XD be a metric space and let A be totally bounded. That is, we have to prove A is now bounded. Now A totally bounded means A must have a finite epsilon net. So we call it B. B is a finite epsilon net, rather one net of A. So B contains finitely many elements, and if we choose finite number of elements from B and radius 1, then the union of all such open sphere covers A. Now as B contains finitely many elements, then the set D of x dash y dash such that x dash y dash belongs to B must be bounded because it contains finitely many elements. So we call it M means max of that. Now for every x and y from A, now as B is the finite epsilon net, or rather epsilon net or one net, and if we choose any 2 points, then there exist points x dash and y dash in B such that x belongs to S1 x dash because it is the epsilon net, and y belongs to S1 y dash. So D of x x dash less than 1, D of y dash less than 1. Now for any 2 points in A, we have D of xy by triangle inequality that must satisfy D of x x dash plus D of x dash y dash plus D of y dash y. So that is less than m plus 2 for all xy belongs to A. So the diameter of the set A is bounded or bounded by m plus 2, so A is bounded. So totally boundedness implies boundedness. Now boundedness may not implies totally boundedness. For this, consider X as any metric space and D as discrete metric. Then prove that discrete metric always bounded, but it is not totally bounded if A contains, or set rather set contains infinite number of elements. Now remember one statement, no proof is not required. Statement is A metric space is totally bounded. A metric space is totally bounded if and only if every sequence has a Cauchy subsequence. Every sequence has a Cauchy subsequence. Just remember the statement. Now the last theorem of this chapter. A metric space is sequentially compact. A metric space is sequentially compact if and only if it is complete and totally bounded. So first part, we assume that the metric space is complete and totally bounded. So XD is a metric space which is complete and totally bounded. So XD is complete and totally bounded, and let Xn be any sequence in X. Okay, now as it is totally bounded, so the sequence Xn must have a Cauchy subsequence. So Xnk is Cauchy. As it is complete, every Cauchy sequence is convergent. So Xnk is convergent. So Xn has a subsequence which is convergent. That means Xn is sequentially compact. Now converse part. Let the metric space Xn is XD is sequentially compact. We have to prove it is complete and totally bounded. Now let Xn be any sequence. As it is sequentially compact, so it must have a convergent subsequence, and we know that every convergent sequence is Cauchy. So the sequence must have a Cauchy subsequence. That means it is totally bounded. This is first part. Now second part, we have to prove it is complete. So let Xn be any Cauchy sequence. So Xn be any Cauchy sequence. So Xn is also a sequence. As it is sequentially compact, so it must have a convergent subsequence. So the Cauchy sequence must have a convergent subsequence. Now we know that Cauchy sequence is convergent if it has a convergent subsequence. So as Xn has a convergent subsequence, so Xn, the Cauchy sequence becomes convergent. So every Cauchy sequence is convergent means it is complete. And that is the proof. Okay. Now remember in this chapter, remember this thing, every discrete metric, if the set is finite, so it is compact. If the set is infinite, so this any metric space under discrete metric is never compact. Also, if X is infinite, then it is bounded but not totally bounded. Okay, so only homework is prove that every sequentially compact metric space is compact, and that's the last theorem of the compact metric space. Thank you.